Yeah.
All right. Good morning. Hope everyone had a good weekend. School Minds is still on their way, but it's officially time. So, all right. So topics for today. So we're basically going to finish Classical Fermions today, and then Wednesday finally turn on quantum mechanics. But so right. One of the important topics for today. Maybe I should outline actually a couple of the things. So I guess there are sort of three broad topics today. So outline for today. So one thing which we almost started talking about, we'll start out with today, is talking about iron fermions. So these are sort of real fermions. We've been studying so far complex fermions. Then we'll talk a little bit about symmetries for Dirac fields. Which means conserved current, right? Still only go through zero for fermions. And last thing is look at some solutions, in particular plane wave solutions to the Dirac equation. Right, we haven't even really solved the Dirac equation yet, right? We sort of labored over how to derive it. There are a lot of different ways to derive it, and ways of breaking it down, right? We saw, if it's massless, basically it separates out. We have these Weil conditions, or Weil conditions. Anyway, but we didn't really solve the Dirac equation. So that's another thing we'll do today. And then, we'll basically be done. Some of the results that we'll need to basically still use just classical results from fermions, you'll do for homework. So there'll be another homework coming later today that's just basically some stuff about gamma matrix identities and playing a little bit with the plane wave solutions so that you get a little bit of a feel before things make less sense when we turn on quantum mechanics. So, right, let's talk about Majorana fermions. So he was a weird guy. I don't know much about him actually. No one does because he was like 28 or something when he went missing. There's a big, I think there are books written about it. I mean, no one really knows how he died. He was on some ferry or something around Sicily and just didn't show up by the time the ferry got to the other side. But he was some student of Enrico Fermi's and discovered this interesting property of fermions that they have another type of mass term that can exist, and it's associated with basically a real sort of fermion. So remember, so our four-component guy, let's write him as maybe something with some index that goes 1, 2, 3, 4. He's a complex object, right? And also, it has to be basically, since any of the Lorentz representations, any of the Lorentz transformations we have are also complex things. So, this idea, right, which I sort of mentioned before, that for Majorana fermions, right, it's sort of the analog of a real scalar field. So far we did sort of the opposite of what we did for scalars. For scalars, we started with real fields and then went to the more complicated and complex case second. But here we started out with everything being complex right away, and now we're going to look at the real case. So it sounds tricky, right? Because let me now impose some condition, that this is real. But then that's not a Lorentz invariant condition, right? I just have another Lorentz transformation on the guy, and maybe he starts out real, but he'll be complex after the Lorentz transformation, right? So right, let's just, maybe we want to just impose psi is equal to psi star. But a Lorentz transformation breaks that. And psi now is complex. So what do we do? Right, the Lorentz transformation isn't going to keep him real even if we start out with it being real. So the first sort of simple way to see how to do this is to write the gamma matrices in a different basis than what we've been using. So we'll use one basically where the gamma matrices are pure imaginary, which is going to imply that the generators for the Lorentz group are real. So that sounds good, right? Then we could impose this, and then any further Lorentz transformations, at least in that representation, are going to give us back something real. That's still not going to be totally satisfactory, of course, because it's a representation-dependent thing, which physically, our result should depend on which representation we choose. So anyway, that'll conclude for what to do next. All right, so actually, there's another reason. So what we'll do. Actually, I guess so far we've only used one representation for the gamma matrices. We use what's called the chiral representation, sometimes also the wild representation. So one can see how to do it, how to have a Lorentz transformation without making things complex. In a new basis Lorentz gammas, which is called the Majorana representation. So I'll write down what the gamma matrices look like there. And remember, right, this is sort of out of a hat, but you can always check that it, at least for it to be a representation of the same gamma matrix, has to satisfy the same algebra, right? So this explicit representation, you can go and check it. Minus sigma 2, 0, and in 3, minus I, sigma 1, 0, I, sigma 1. Actually minus. So then that's called the Majorana basis or Majorana representation. So right, well, upshot is still satisfies. It looks very different than the one we had before. It still satisfies that anti-commutator has to give me 2 times the metric. And the whole point of this representation, the reason why this is going to be what we want, right? Because we want to have Lorentz transformations that don't change a guy who starts out real and make him complex. So what's special about it is that complex conjugate of a gamma matrix is minus gamma. So, or in other words, pure. So that means, remember our generators, what we'll call the Lorentz generators. Those are the guys that make up Lorentz transformations, right? Those, one representation of them when they act on spinors was, well, this is mu nu, sorry, was that it was, I always forget the prefactor, but it's a commutator. So it's the product of gamma matrices. So something that's pure imaginary squared is going to be pure real. So these are pure real generators in this representation. That's the point. So then at least, as long as we start in this basis, we can do the naive thing for making a spinor field real, which is just say, now impose the reality condition that he's equal, the spinor is equal to a complex conjugate of himself, and now any Lorentz transformations aren't going to change that, not going to break that. So this sort of gives us a hint that maybe there is some way to make a spinor real. So far we've only been able to see it in one representation, but can we do it more generally? Is there a more general basically, I guess what I'm going to say is there a more general definition of a real fermion? One that doesn't rely on choosing some specific basis. So there is all that we're going to, it's at least a little bit more general. So all we're going to require, we're still going to require some properties of the representation. We'll require the dagger of gamma 0 is gamma 0, and the dagger of gamma I is gamma I. And what's going to change also is this definition. We're not going to, this won't be sufficient more generally to require that this guy always stay, it'll basically be a real field. There'll be a new condition, which is called a Majorana condition. So everything connected to this is named after him. And it's basically going to be some generalization of this. It's going to be, we have to define basically the charge conjugation operation. So there'll be a new operator that we define. So be the new define charge conjugation. So this is the C of CPT. You probably have heard of, maybe you've heard of the CPT or CP, those famous things in the standalone. So this is the C of that. This is defined. We'll write it with a little c. Sometimes you will have parentheses around the c, sometimes not. But it's defined as almost what we were looking for. But now this is some matrix, who also will be a representation of the thing. So what we did just a second ago was actually write down the correct condition, but in a representation where C is 1, in that Majorana representation. But this, now defining, this is a charge conjugation operation. We'll see, representation, independent way to define what it means to be Majorana. And this will need to satisfy CC dagger is 1, and also C dagger gamma mu, C is minus gamma mu star. So these are crucial to show. We're not going to show that, but it actually, it's not a lot of work. You can show that these conditions imply basically that under a Lorentz transformation, this new field, this charge conjugated spinner, transforms in exactly the right way. Now that I can use the same generators and everything that we know for, and that boosts are the same, but, or sorry, the other way around. Rotations are the same for left and right, and boosts are different. Anyway, you can show that those conditions are required to give you the right transformations. And now the Majorana condition, instead of this, condition is just that psi equals psi c. So it's certainly going to eliminate some degrees of freedom. Basically, it exactly halves the number of degrees of freedom. We'll see that explicitly. So this is, the upshot of that is it's a Lorentz reality condition. Reality just in that it's real. Real, not complex. So, right, we saw an explicit form of C, which was 1, so that's a pretty boring one in the Majorana representation. In our more familiar representation, we can also write it down. What about the C matrix? So, we already saw C in the Majorana representation. That's just 1. So that really imposed the Majorana condition, and that's really just the same thing. Psi equals psi star. So that's sort of boring. Let's go now, right, I mean, we've developed everything in the chiral representation before, so you can get better intuition, I think, by going there. And there, the C matrix has a different form. It's I gamma 2. And gamma 2, right, was someone depending only on the second Tally matrix, minus I sigma 2. So now, basically, right, we want to impose psi c is just psi, and use our notation psi is u plus u minus for the left and right components. So then this becomes, right, if I'm multiplying things out, I have minus, not a minus, I sigma 2 minus I sigma 2, 0, acting on u plus u minus, and that all has to be equal to u plus u minus. Right, so now this is what the Majorana condition looks like in the chiral representation. I choose, writing the 4-component spinner as a stack of two component spinners. So right, what's that going to do? It'll give me that I sigma 2 u minus is u plus, and minus I sigma 2 u plus is u minus. So in other words, these are the same condition basically. In other words, I can find my Dirac spinner, the 4-component guy. I can write it in terms of the undetermined u plus. Once I fix u plus, I know what u minus is, right? That's the point of what the Majorana condition tells me. So it tells me now I know the bottom component. It's I sigma 2. Sorry. Times u plus. So this is how people, maybe sometimes actually when they first introduce it, will say this is what we mean by a Majorana fermion. So sometimes too this is also called the Majorana condition, but this is really a representation dependent, right? So you can see why we have the number of degrees of freedom, right? If psi originally is 4 components, like he is in the more general case, when we don't impose that condition, now we've halved it exactly, right? Now he's all determined by 1, 2 component spinning. So right, you obviously also can't apply so the Majorana condition and while condition are exclusive things. You can't apply them both at the same time. The while condition was basically either u plus was 0 or u minus was 0. Remember we had that before. So these are mutually exclusive. Majorana and while are mutually exclusive things. You can't have them both. You can also check that, for example, if you start out, right, we haven't said anything about the Dirac equation, that we satisfy the correct equations of motion. But if I start out with a sign who does satisfy the Dirac equation, I can check that this conjugated field also satisfies the Dirac equation. And once we impose quantum mechanics, which we'll do a bit later, but after quantization, this condition basically implies that the particle and the antiparticle are the same for this state, which makes sense thinking about it, like from the degree of freedom perspective. So the only field for which that could be true in the standard model is maybe the neutrino. I mean, if you're your own particle, you can't impose this for anyone who has charge. If you're your own antiparticle, you can't impose that for anyone who has electric charge. Right? So the only neutral fermions in the standard model are the neutrinos, so we don't know. It's a very hard property to probe, but maybe someday we'll see neutrinos double beta decay or something. Will tell us. Okay, so enough about Majorana fermions. So let's talk about symmetries. Yeah, maybe actually something I could talk about. Still talking about Majorana fermions. Maybe we'll try to show too that if we're about to talk about symmetry, Majorana fermions break any sort of U1 charges, things like electric charge. I mean, that's pretty obvious from what we said before, that they have to have their same particles and antiparticles have to be the same. But it's even more general than just electric charge. So maybe we'll be able to see that. It holds for any what we'll call vector charge. Symmetries and conserved currents. Alright, sorry, I probably should ask before starting, but any questions about Majorana fermions? We didn't actually look at their mass term, but there is another, a different way of writing a Lorentz invariant mass term, calling that conjugation field. But yeah, maybe we'll come back.
Can bound states of particles be Majorana?
Yeah, that's a good question. I guess in principle, yeah.
Okay.
Yeah. I don't know if that's realized in nature.
Yeah. Okay.
Yeah. I mean, there is something called neutron-antineutron oscillations people look for.
Okay.
Which I guess would be manifestation of that.
Okay.
But yeah, so right, in principle, right? I mean, nothing we wrote down necessarily assumed that they were fundamental. It could be a useful way of writing down some fermion state. Maybe it's built out of ground state or something like that. But right, so let's recall the most important thing about these, why these topics are connected, which is the Noether theorem. Says, right, that symmetry will imply a conserved current. And in particular, what we wrote was in our 4-vector notation. This means that there's a conserved current, where this J was some charge density and some current, right? So this really implies that it's conserved. It just says the density is changing in time. That means it's outflowing. It means there's some gradient of the charge out, right? That's what this condition implies. And we found for scalars, and it's exactly the same equation. We found that the conserved current had the form, look at the Lagrangian, take a derivative with respect to the derivative of the field, and multiply it by how the field changes under some infinitesimal transformation, and subtract away some part that maybe could have given you a total derivative in the Lagrangian. So, just to remind us what those things mean, we were saying under this transformation, under this symmetry transformation, phi might go to phi prime, and he's just ordinary phi, but plus some small parameter and a delta phi. This is some infinitesimal parameter that we're using to say we just do some tiny amount of transformation under the symmetry. And the Lagrangian, we allowed to vary up to a total derivative. That could go to alpha d capital J. So, yeah, this little alpha is just an infinitesimal parameter to control that. We're looking at the smallest possible transformations under the symmetry. So right, so that was the whole story basically, you know what we're saying, right? You have a symmetry, we know general prescription for how to get the conserved current out of it, looking at how the field changes and how the Lagrangian changes. So there are a couple cases we can look at. So the first one that we always can look at, right, is the one that will give us conservation of energy and momentum. So that follows from space-time transformations, space-time translations. So that one's for everyone, right? We can always do that. We look at space-time translations. So these are things like just take your position, your 4-vector, and push it over by some epsilon amount. So that means the spinor field is going to change by an amount proportional to that. And the only thing I could contrast this special vector that's the symmetry, the space-time transformation with is the derivative. That makes sense. So this is also saying that the derivatives are the generators of space-time translation. So this gives 4 conserved currents. They have 4 ways of translating the thing. So we get 4 conserved currents. So I have basically an extra index. I guess actually usually write it down there. Right? It seems kind of confusing, but right, remember, this is for one current. It's a 4-component guy because everyone's 4-component in our world. But since I have 4 separate transformation properties here, really I also get 4 currents, so that's why there's an extra index on them. But usually we use instead the notation that this is T mu nu, the stress energy tensor. And for this specific transformation, then we just use our general Noether's theorem. We'll have take a derivative with respect to the derivative of psi, and now multiply by that delta phi, how much the field itself has changed. And remember, the way we've defined it is it's you don't include the infinitesimal parameter in front, right? That we've factored out. And we have one piece that's Lagrangian too. I didn't write that down, but also you can check that that also is the same. When I vary with the space-time translation, the Lagrangian itself changes by basically derivative of the Lagrangian. So. Right. And also, right, notice that, let's look at the Dirac equation. So L, the Lagrangian for the Dirac equation is psi bar, mu, minus m, psi. So I only have d psi, I don't have d psi bar, right? So I can write T mu nu, the same guy, is I, psi bar, d mu, gamma mu, psi, minus theta mu, Lagrangian. And moreover, if you impose, so far we haven't said anything really about this field configuration necessarily satisfying the equations of motion. But if you impose right, the equations of motion, which are the Dirac equation, if you impose that, you can forget about the Lagrangian part. So, which means then at the end of the day, with T mu nu, well, really only need the energy part. We'll come back to it, especially for historical reasons. So that is some confusion. Dirac's original interpretation of the Dirac equation. So we don't have to worry about that here. So we in the new side. And in particular, the energy one is the most interesting. T00 part, which is always the energy or energy density. Actually, write down total energy. Would be remember this is a density, basically, right? So to get the total energy, we have to do the integral over all space. And right, we could just use. Oh yeah. Yeah. Oh, sorry. I wrote something wrong, I think. Yeah, sorry. Right, it's supposed to be a derivative Yeah, it's unfortunate gammas and partial derivatives look so similar. But right, this is really a derivative. So when we take the 0, 0 component, we get this for the energy. So, or in other words, we could write this as gamma dot. So this is really the final expression for the energy that you can always use for fermion. And we'll come back to this. So you may have heard of the Dirac hole theory. So he was very confused when he first encountered these things that looked like antiparticles. And he was a little confused because he was sort of doing things quantum mechanically properly. So he sort of came up with a classical interpretation of how to make sense of antiparticles, which had to do with the fact that this can give you negative energies associated with the antiparticles, which can be confusing, but, and we'll examine that actually. We'll do things sort of the naive way first, the way Dirac was doing it, and see the problems it leads to. So we'll come back to that. So the another important symmetry is what's called they're called internal symmetries. This is one that's vector type. So the reason it's called internal is just that it's not associated with anything having to do with space-time. Some internal properties of the fermion itself. Something like charge. So, right, this is really along the same lines as what we encountered something like electric charge when we were talking about complex fields. So this is sort of the analog of that. Because notice that the Dirac equation is invariant under a phase shift. What's the Dirac equation? I gamma partial minus m psi. Notice that's invariant under psi goes to e to the minus I alpha psi. So this is phase rotation. So in other words, too, right? To connect with the Noether theorem, right? I would use the infinitesimal version, which tells me, the thing that's going to be appearing in Noether's theorem. So what this means, so that the conserved current, which we'll label with a V, gamma bar, psi bar, gamma mu, psi, and nothing else. And that V is for a vector. Right. We talked about it before too, but basically, vector, since the left and right components are treated the same, we'll encounter in a minute similar sort of symmetry that it's explicitly different. It doesn't treat them equal footing. So is it clear how you would get this? Just get it straight from the Noether theorem again. There's no change in the Lagrangian, so that term is 0. It's also easy to check explicitly. You check that it's conserved. For just using the equations of motion. So we take the derivative on the vector current. So, right, the derivative can act on either psi bar or psi. Gamma is constant. So let's just show that quickly. So it could be, if he passes through psi bar, then he'll hit psi. And we can use the equations of motion, which are, right, I m mu d minus m. Psi equals 0, and minus I for psi bar. Right, so in other words, right, means I gamma mu d mu psi is m psi. So we have an expression for how to treat the derivatives that are appearing there. We can stick those in to get the derivative of the vector current is just Im psi bar psi and minus psi m psi bar psi. Or in other words, 0. For whatever m. The m doesn't matter, it's always going to be 0. So it's indeed conserved. And it's often nice to have an explicit form for the charge. By that is d0 rho minus that whole thing's 0. So this is sort of the the lump of charge with some density associated with the no third current. So oftentimes want to work directly with the charge. With the Q associated with rho, basically. And that's just the space integral overall space of rho. And rho for us was just the 0th component of that 4 vector current, right? So d3x psi bar gamma naught psi. But remember, what was psi bar? Psi bar was gamma naught dagger of psi, and gamma naught squared is 1. So you can write out or in other words, this is 1, so current is just psi dagger psi. So this is basically the electric charge slash particle number. So it looks very much like a number operator, right? So this is really when we start studying gauge theories like quantum electrodynamics, this is the current, the exact same current that appears there. So it is really the electromagnetic current. But, also appears in other theories. So the more general name for it is just the vector current. So you might guess that there's a related one called the axial vector current, or associated with an axial symmetry. But that's special because this condition will be violated. Basically, I'll get, instead, because I have gamma 5s, that cancellation won't work. I'll have a plus sign there. So you'll see that it'll be proportional to, it won't be a conserved current unless the mass is 0. So it's a sort of a special thing, which we sort of maybe should have anticipated in a sense, because we knew if I set the mass term to 0, there's the left and right field really don't talk. Right? So there's sort of an extra symmetry associated with that fact, and that's this axial symmetry. So you have to have a Fermion's massless. So if you have that, there's an additional symmetry. Where psi goes to, instead of just a phase, it's phase times gamma 5. And psi bar goes also to the I. Well, sorry, on the other side. Remember that what was gamma 5, he explicitly treats left and right differently. So this really implies that left and right are not on the same footing. They transform oppositely. Opposite. Take opposite as 3D. So if we're looking at this symmetry, this axial symmetry, the new current that we get, we'll call him J mu, but with that A label. That one is gamma mu gamma 5, which is not hard to see, right? If you do the infinitesimal transformation, it's the same thing basically as the vector one with an extra gamma 5 there. So you can check he has the right transformation properties of an axial vector under parity, for example. Really an honest axial vector. And right, we can do exactly the same thing. Let's check that it's conserved. So let's take the derivative on J mu A. We'll have all the same things involved. Derivative on mu, but then I have a leftover part, or I have the derivative acting after the gamma matrices. So right, exactly the same steps, except now that part having to do with the mass doesn't fall out. And I have a leftover fermion bilinear with a gamma matrix in the middle. So only conserved if n is 0. But as long as m is small, you'll be able to effectively use it as a symmetry. Right. So that is an amusing thing. So in classical gauge theories or classical electromagnetic-like theories, have an axial symmetry associated with them, axial vector current. But quantum mechanics violates it or destroys the symmetry. So, right, this is we encounter something like this in the standard model too. We we say that the axial vector symmetry in the standard model is anomalous as a result of this. It's something that appears to be a good symmetry at the classical level, but that's violated by quantum theory. So this is called, anything that has that property is called an anomaly. And there are useful tricks and things too for how you ensure that your quantum theory that you write down isn't anomalous. You don't want to accidentally have weird things going on with gauge symmetries being violated by quantum effects. It basically just shouldn't really be called an anomaly. What it really is it's not a symmetry in the real world, in the quantum world. So, yeah, so I think that's all there is to say about axial symmetries and symmetries for now. So you can also basically use Noether's theorem one more time to look at the what's required of the field, or what's the currents associated with Lorentz transformations on spinors, and that will give you that it has an interesting spin dependence. You can see why it has spin a half, but we won't do that for now. But let's also look at some solutions, right? We haven't solved the Dirac equation really at all yet. So, just like we had in mind for scalars, it makes sense to start with the simplest thing. It makes even more sense to start with plane wave solutions, not only because they're the simplest thing, but also because, right, this is sort of our strategy for what we're going to do when we quantize things, right? We do this expansion in normal modes or plane wave solutions, so let's start with those. So this is still all classical, right? We're going to study solutions to the Dirac equation. The same guy. So in particular, what we'll do is, make an ansatz and see what it requires. So we'll use this ansatz. Side is only depends on the 3 vector. E to the minus I px. So this is some 4 vector spinner. 4 component, I guess, sorry, not 4 vector. Some 4 component spinner that can depend on the momentum. So we can put that in to the Dirac equation. And let's use again our chiral basis. So we have an explicit form for the gamma matrices. Then the Dirac equation becomes first of all, right, just like we had always with plane waves, a derivative then is really a momentum. So we can write this as gamma mu p mu minus m. That's really the Dirac operator. Acting on u of p. That's now using that notation for, or the chiral representation for the gamma matrices would give me just a -1 secretly. Let me write this a better way. Secretly, right, there's an identity there. So when I write this 2 by 2, it will be a -n and p mu gamma bar gamma mu, p mu, and minus m. So that's the Dirac equation, right? Just using that for our in the chiral representation. And also, right, in case it's still weird, these guys mean stick a 1 together with the 3 Pauli unities, or stick a minus 1. Right. Put a minus sign on the Pauli vector. All right, so this is now, we can think of this as the core requirement for our plane wave solution in the chiral basis, the one we're most familiar with. So I'm going to write down a solution and we'll check it. So claim the solution is star. Let me write it. This is equation star. Has a funny looking form. It's P dotted into sigma, and then P dotted into sigma bar. So that's the solution. So let's check. This is true for any guy. Two-component spinner. That is properly all right, so let's check that. So we'll do this. This ansatz was with either the plus, or sorry, I guess it was each of the minus IPX. So we'll do the same thing. These sorts of plane wave solutions are called positive frequency solutions. We'll do basically the same sort of ansatz for the negative frequency solution. We'll skip how to go through and see that this is the analogous stuff for the negative frequency, that this is the right form. Okay, so that's right. U1, U2 for our spinner. Right. So what do we have? So we have minus m mu mu, or we can just write it actually. Like we're writing there, which is P dot sigma and P dot sigma bar. Right. So, all right, we can just do that out. So we'll get P dot sigma acting on U2, going to give us mu1, and also P dot sigma bar on mu1 is mu2. So we can choose either one. Either of these implies the other. Something you'll show a useful identity, but else is not super hard. You can see that either of these implies the other. since p dot sigma times p dot sigma bar, that is equal to m squared. Alright, so this is where we want to work on. We'll try to show this using this nonsense, but U1, we guessed at first it's proportional to P dot sigma. I have some new two-component spinner. So, right, we start with, say, the bottom one. So then if we have P dot sigma on U1 equals MU2, what is that going to mean? Well, so right, if I just insert this, so I'll have P dot sigma bar, P dot sigma, C prime, that's equal to MU2. And this thing, now, that we'll show later for homework, this thing is m squared. So, U2 is just MC prime. Which actually, so this is enough to see that we basically proved the result, because our U P then has this form. Anything, right? We could have any prefactor here, any A, if we want. Some constant in front, it's not going to change. These requirements still hold. So we can also, those requirements imply that U1 has to be P dot sigma times something, and the bottom part is the same something but times the mass. So anything of that form is going to solve that equation star. We erase the version of the Dirac equation. Where A is some constant. But to put it in exactly the form that I wrote before, you can make this more symmetric too. So let's say we make a specific choice about A and C prime, which have to just be constants. So let's make this more symmetric. Take A is 1 over the mass, and C prime is square root of P dot sigma bar times C. If we do that, then what do we have? Right, then we have U1 is P dot sigma, we have there, but now times C prime, square root P dot sigma prime, sigma bar of C. And, right, this is the same as m times P dot sigma. Again, using P dot sigma bar is m squared. So finally, write that in that more symmetrical. The plane wave solution has that form. Rather symmetric. And you can leave it like that too. It's easier. Probably depends on the circumstance. But this will usually be the form that we take for the plane wave solutions with the positive frequency. Remember, right, so this is with the solution to Dirac or psi being 2 e to the minus I p. Okay, so there's one solution. The obvious other question is what happens if that guy is a minus sign upstairs, makes the whole thing positive. So things follow through basically identically. So it'll work actually with spinners of this form on the homework. You'll get more familiar with some of the identities that make bigger calculations like we'll encounter when we quantize things much easier. Right, this type of ansatz is called positive energy, so positive frequency, positive frequency solution. So we'll also look at negative frequency, and that'll be the last thing today. Right, so there are other solutions, which are basically the analog with -9. And there the spinner is called V, instead of U. When we quantize things too, we'll see that U and V will represent particles and antiparticles. So here, the Dirac Equation is required. That the four components V so again, gamma mu and p mu. The derivatives are just that is m p mu sigma mu and p mu sigma bar m acting on v. That whole thing is 0. So it's basically the same except for the sign on the mass term. We can go through all the same steps, but I'll spare you that. Solved by, again, putting it in symmetric form so that both components look sort of the same. Square root of p dot sigma. We'll call it eta instead of c, and a minus sign. P times p, that's p times sigma bar. Where this guy again is two component who is properly normalized. All right, so there'll be, I think go over one or two more sort of calculational properties of these sorts of spinners next time on Wednesday, but we'll really start in with quantizing the theory. So we'll get more back to the main path, of course, which is quantizing fields. Because right now we had a big detour towards talking about classical fields, but fairly involved classical fields that have this intrinsic angular momentum. Next we'll try to basically just go back, maybe one thing to do if you have spare time is go back and look over what we did when we quantized the scalar field, because that's how we're going to proceed with the fermion field. We're just going to try and copy and paste basically from what we did for scalars, and we'll see that it fails. But it fails in an interesting way. And the interesting way basically indicates that there is a deep connection between spin and the statistics that the particle obeys, whether it obeys Fermi-Dirac statistics or Bose-Einstein. And that was important historically too. It led to a lot of confusion for a while about how to quantize fermions. So we'll do it the wrong way first, which is illuminating, and then figure out what we need to do to make things right. Which will basically show us that it is really a spin 1/2 field and obeys the Pauli exclusion principle and all that. So that's next time. And we'll, shortly after that, be able to go back to the sorts of find the diagram processes we had for complex scalars. This, what did we call it? Phi, psi bar theory. That was all just scalar fields, right? But now we can redo the same thing with fermions, where basically we had the same diagrams and everything, but now with fermions doing the scattering. It's still being controlled by the mediation through a scalar exchange. And that's almost to real QED, but not quite. But right, so there'll be another homework coming later today, so check it out. And see you on Wednesday. Copy? Yeah.
अलि धीरे गरे जरा आएगा बोलिए तू करे है ना बोलिए